So folks, in the last video we looked at solving this system right here, and we did it with Gauss-Jordan elimination. Now we're going to solve this system by matrix inversion. So remember that the idea is we're going to put this in the form of matrix A, which will be a coefficient matrix, times a matrix of our unknown variables is going to be equal to a constant vector. Okay, so in this case the dimensions of this will be a 2 by 2, and we're going to multiply it to this. This will be a 2 by 1, and the result will be a new 2 by 1 column vector. So let's go ahead and set up this system. Our coefficient matrix will be 3, 1, 2, 5. And we've said then that this system is going to have a unique solution provided we can invert this matrix. And if we can invert this matrix, then we will simply multiply both sides of this equation by the matrix inverse. That is, if A inverse exists, what can we do? Well, we can take and multiply the left-hand side by A inverse and the right-hand side by A inverse. And as we've noted before, make sure that you multiply by A inverse, first of all, always on the same side, but second of all, on the, in this case, it would be on the left, so that when I regroup this multiplication here by my associative property of matrix multiplication, what we end up with is just the identity times x is equal to A inverse B, or just that x is equal to A inverse B. So we're going to do this procedure on this system. So what do we need to do? Well, we need to find A inverse. So let's go ahead and find A inverse, and I'd like to do so using the shortcut technique. We now have a little bit better vocabulary, so I'm going to say that it's 1 over the determinant of matrix A times, and then what do? We swap these two entries, so 5 and 3, and change the sign on these two entries. Again, remember, this isn't what an inverse is, but it's a formula that gets us to the same expression as if we did the Gauss-Jordan elimination on this. So let's see here, we're almost done. We just need to go ahead and convert or calculate the inverse of this matrix, the determinant of this matrix. And the determinant of this matrix would be 3 times 5 minus 2 times 1, which comes out to be 13. So we have that A inverse is equal to 1/13 times 5 negative 1 negative 2 3. So our inverse matrix is the matrix 5. Oops, that's pretty ugly. Our inverse matrix is the matrix 5, 13, minus 1, 13, minus 2 thirteenths, and 3 thirteenths. So now what am I going to do? Well, now that we've computed what A inverse is, we're going to return to our matrix equation. So let's go ahead and put that back up there. In fact, I'll just grab this. Okay. So now that we have this, here's our matrix equation. We've just computed A inverse. We're going to multiply both sides by A inverse to give us that xy is equal to 5 thirteenths minus 1 13th minus 2 13ths, 3 13ths. This was matrix A inverse, and we're still going to multiply this to B here, which is the matrix 6, 17, or if you like, the column vector 6, 17. So we find then that xy is equal to, and we do this multiplication, so let's see here, this will give us 30 thirteenths minus 17 thirteenths for the first entry, and we get minus 12 thirteenths plus 51 thirteenths for the second entry, or that xy is equal to 13 thirteenths and 39 thirteenths. And so we find at long last that xy is the column vector 1, 3, which is the same answer that we got in the previous video when we did this with the Gauss-Jordan elimination.